Okay, so for what we have in working with eigenvalues and eigenvectors, we have in the continuation of these topics, okay, we have the characteristic equation, which will be a key component in evaluating what are regarded as eigenvalues. And we have, as an example of determining eigenvalues, we have a given 2 by 2 matrix A is equal to, where we have in the first column we have 2, 9, second column we have 1, negative 6, and again just with familiar algorithms, okay, again we have A minus lambda I, where we have the quantity of that times x is equal to 0, and in initiating the pathway to the determination of eigenvalues, okay, we have first of all we have A minus lambda I, so you have A given as once again 2, 9, 1, negative 6, and for the identity matrix multiplied by lambda we have lambda 0, 0 lambda, and just taking the difference, and we have with the corresponding parts, okay, we have the first column in the difference matrix to be at 2 minus lambda, 9, 1, negative 6 minus lambda. And in looking at the determinant of this difference and setting to 0, okay, so we're looking at taking the product, okay, so you have 2 minus lambda, quantity times quantity of negative 6 minus lambda, and we have minus 1 times 9 is equal to 0, and once we combine like terms, we have in expanded form, we're going to have lambda squared plus 4 lambda minus 21 is equal to 0. In the factored form, we have the quantity of lambda plus 7 times the quantity of lambda minus 3 is equal to 0. And both of these forms here, whether expanded or factored, will represent the characteristic equation. And we have with the zero product property, or if you were to use the quadratic formula, we would have the values of lambda would be at negative 7 and positive 3, and these two quantities are going to be the eigenvalues for this particular 2 by 2 matrix. Now, let me mention something for a given matrix. Okay, rule of thumb here. Now, we've been looking at triangulating matrices with triangular formations of zeros in the case of evaluating determinants. But for the determination of eigenvalues, never use the echelon form of a matrix. Okay, now we have with our first example, okay, we have 2, 9, 1, negative 6, and if I were to put this in echelon form, I would have 2, 0, 1, and negative 21 halves. Now, for the original matrix A, again, the eigenvalues, we have at negative 7 and positive 3. And if I were to take the eigenvalues or determine the eigenvalues of the echelon form of this matrix, I would not have the same eigenvalues. If I did, it would be just one of those rare cases. So just taking this particular matrix, if I were to look for its eigenvalues, so we have as a second example, okay, we have A this time to be 2, 0, 1, negative 21 halves. And looking at what we have once again for A minus lambda I quantity times x is equal to 0. Okay, we have for A minus lambda I, again we have with the formation, again you have like this minus lambda 0, 0 lambda. Difference we have at 2 minus lambda 1 for the top row. Bottom row we have 0 and negative 21 halves minus lambda. And if I were to take the determinant of this difference, okay, what would happen here is that I would have 2 minus lambda quantity times negative 21 halves minus lambda quantity is equal to 0, and we can say that this factored form represents the characteristic equation. And just like the first example, you could also have the expanded form, but the factored form will suffice. So this would be our characteristic equation. And notice we have utilizing the zero product property. If I were to set each of these factors to 0, instead of having negative 7 or 3 as eigenvalues, I have instead 2 and negative 21 halves. Okay, so again, never translate a given matrix A in terms of its echelon form. to get eigenvalues. You can use it for determinants, but never for eigenvalues. And this second case, all right, so again, the eigenvalues are totally different, whereupon we had the values at 2 and negative 21 halves. So just to repeat again, never use echelon form of a matrix if determining eigenvalues. However, you may use echelon form for evaluating determinants. Totally different exercise. Now, third case, all right, so going from a 2 by 2 to a 3 by 3 matrix. Okay, say we have A to be a 3 by 3 matrix, and going column by column, we have 1, 2, 0, 0, 3, 6, negative 1, negative 1, and 0. And utilizing our equation, so we have A minus lambda I quantity times x is equal to 0 for A minus lambda I. Okay, so I have, again, I have first column 1 minus lambda 2, 0, second column 0, 3 minus lambda 6, third column have negative 1, and 0 minus lambda, which comes out to negative lambda. And looking for the determinant of this difference and setting to 0. So it's going to turn out that that for the characteristic equation, that is going to emanate. All right, so again, you have 1 minus lambda times the determinant of the 2 by 2 determinant that corresponds to, we have 3 minus lambda 6, negative 1, negative lambda. Now all the other determinants are going to head to 0. So the only non-negligible determinant will be this particular section where we have multiplied by 1 minus lambda. And looking at multiplying 1 minus lambda times the quantity, 3 minus lambda times negative lambda, and then we'll have minus negative 1 times 6 or plus 6, and distributing, multiplying out, and expanding. Okay, so we have the quantity of 1 minus lambda times the quantity of lambda squared minus 3 lambda plus 6. Quantity is equal to 0. Now, if I were to expand, okay, now we have the characteristic equation will end up being at negative lambda cubed plus 4 lambda squared minus 9 lambda minus 6 is equal to 0. Now, this one cannot be factored into rational terms. And with the computational device, now the approximate eigenvalue will be around negative 0.53. Right. Now, again, just to restate, okay, never use echelon form of a matrix if determining eigenvalues, but you can use it for evaluating determinants. Now, for the third example, if I were to take, say, the echelon form, okay, I would come out to 1, 0, 0, 0, 3, 0, negative 1, 1, negative 2. And in this particular case, all right, so I have a triangulation of zeros. And let's say if I were to set A equal to the echelon form of the matrix in example 3, so just running it through the process. Okay, so I have A at 1, 0, 0, 0, 3, 0, negative 1, 1, and negative 2. For the difference, I have, again, the diagonal array 1 minus lambda, 3 minus lambda, negative 2 minus lambda, and taking the determinant, okay, and setting equal to 0. And what I'm going to have here is that the only non-negligible portion, again, is going to emanate from taking 1 minus lambda and multiplying by the 2 by 2 determinant, okay, where we have 3 minus lambda, negative 2 minus lambda, taking that combination and multiplying by 1 minus lambda. And I can just leave in the factored form and for what we have in this particular case. All right, so once again, we can say that this is going to be the characteristic equation, and for what we have with these distinct factors, so you have 1 minus lambda times 3 minus lambda times negative 2 minus lambda. So from this, okay, we're going to have integer valued eigenvalues. Okay, and it doesn't matter what order you place those in, but we do have 1, 3, and negative 2 among the values.